Alright guys, welcome back. Now I'm going to give you a little, I hope you've all watched that maybe 5-minute video on the kinetic molecular theory. Okay, and what I did is in the notes here, I just want to remind you of the 3 states of matter and how molecules are arranged. Molecules are constantly in motion, and really if they're in motion, right, so I'm just going to write this here. This is called KMT, kinetic molecular theory. Okay, so the word kinetic means motion, right? So all molecules are constantly in motion. Okay, and if they have motion, so if molecules, if they're in motion, they have kinetic energy, okay? Because kinetic energy is the energy of a moving object. Well, if a molecule is in motion, it has kinetic energy. And since anything that has a temperature above absolute zero, which is everything in the universe, that means that matter is constantly moving somehow. Okay, now in a solid, they just sort of vibrate back and forth like this, okay? In a liquid, they sort of slosh around each other in the liquid, right? And then in a gas, they're able to zip all around, all over the place. And then you can see in these pictures here, like some representation of how molecules move in all 3 states of matter. Okay, so now let me define these terms. 1, thermal energy. Now I mentioned in the other video, thermal energy is the total EK of the molecules in a given substance. Okay, it's a total, okay? 2, temperature. Temperature, often confused, okay, is a measure, often confused with thermal energy, measure of the average, okay, EK of the molecules of a substance. Okay, so that's one of them is measured in joules because it's energy. Now this one is a measure, and we have different measures: degrees Celsius, Kelvin, Fahrenheit, but let's stick to metric, so degrees Celsius, and Kelvin is preferable, all right, because like 0 Kelvin means it has no kinetic energy at all, and you can't never get anything at 0 Kelvin, but I mean 0 is 0, right, whereas degrees Celsius is based on the freezing point and the boiling point of water, so you can get negatives. That doesn't mean there's negative energy. That doesn't make sense. You can only have positive amount of energy, okay? You can't have less than 0 energy, but you could have a temperature that's less than 0, but that's just because of the way it's being measured. Kelvin is better that way, okay? You can never get a negative Kelvin temperature, for example. That would make no sense. So it's better representation of what temperature really is, okay? So here you can see the difference between the two. Thermal energy is a total, but temperature is an average, okay? And then 3, heat. Heat is a transfer of thermal energy. So that's what heat is. Wow, why do I keep doing that? It's too much French in my house. Okay, so heat is a transfer of thermal energy, and I actually included a little diagram here. I'm going to see if I can move it into the picture and make it a little, maybe make it a little bigger if it'll let me. All right, so let's just look at this picture for a second. There's actually 3 ways, okay, of transferring thermal energy from one area into another. One is by conduction, okay? So you can see here the pot handle gets hot. Okay, so you heat the pot handle gets hot, and if you've ever held a metal pot before, we have an iron skillet, and it's the handle's made of iron, and so you pick it up, If it's been on that heater long enough, that handle gets incredibly hot, and you have to be very careful how you handle it. Okay, so let me explain conduction. Let's go A here. Conduction is a heat transfer. Here, you know what? Let me write it like this. E, energy transfer by direct contact. And this is where collisions take place between the molecules. Okay, so that handle gets hot because it's attached to the pot. And so what happens is the molecules in the pot here conduct the heat down to the end of the handle, just because the hot molecules in the pot will hit the molecules in the handle, and then the molecules in the handle hit each other, and then it's sort of like domino effect. That heat just conducts its way down to the end of the handle. Okay, so that's conduction. So B, convection. Convection is what you're seeing in the liquid here. Okay, so here we call those convection currents. Okay, and what happens in a convection current, I'll use a rainbow color here, is you get, actually I'll start at blue, like this. Yeah, what happens is, actually, let me start with the rainbow color. So here, that's perfect actually. So what happens is, molecules that start off cold but get heated at the bottom rise to the top because hot liquid and gas is less dense than cooler liquid and gas. But then what happens here at the top is you get this sort of taking place where it cools off here and then sinks back down to the bottom. We call these convection currents. So let's say there's heat down here at the bottom and there's cooling taking place at the top. Well, cool air, this is exactly what happens with atmosphere, let's say. So cool air falls, hot air rises, okay? So this is the hot air rising over here. Hot air and cooled air get exchanged, and so there's a transfer of heat by just the varying densities of hot and cold liquids. So convection only happens in liquids and gases, not in solids. Okay? So convection, this is energy transfer. By differences in density between hot and cold, so whereas different temperatures, fluids, like for example, liquids and gases only. Okay, like what does a hot air balloon do? Well, it rises. You know, if you want to get it to go down, you got to cool it off. Now it'll cool off naturally as you go higher and higher up in the atmosphere because space is very cold. So the closer you get to space, the colder the air gets. Okay, and that's why it's like minus 60 up there where the airplanes are flying at, 40,000 feet or whatever. So it gets really cold, and then if the hot air balloon gets cold, of course it'll come back down. Okay, but if you heat up the air, it rises, and that's why you'll see hot air rising over a barbecue. That's why the sun creates wind by convection current. It heats the earth heats the atmosphere, and then that hot air rises and cool air falls down from the upper atmosphere, and this creates a convection current, which is why at nighttime usually the winds calm down, depending on the weather and a few other things, but yeah. All right, now finally, radiation. Now radiation is light, so this is light energy, okay? The hot air above the flame rising up to heat the pot is convection, but radiation, the light itself coming from the flame, that is radiation. So, oh gosh, what am I doing? C, radiation. Okay, radiation is energy transfer. By emission, probably spelling that wrong, of light. Okay, so there you go. When you're sitting in front of a fire, there's hot air above the fire, but you can feel the radiant heat. That's when, like, if someone sits in front of you in front of the fire, you'll feel a lot cooler because they're blocking the radiation that comes from the fire that you're sitting in front of. Okay, so radiant heat. You know, just as an example of this, I wanted to show you this. Okay, I'm actually going to copy a picture here from the internet. Okay, so just give me a second. The construction of a thermos. All right, so I'm going to copy this image and I'm going to paste it in your notes. Okay, right here. All right, so why am I showing you a bottle? Well, what's the purpose of a thermos? Well, thermos is a company name actually, but the bottle that they make, that they're famous for, is an insulated container. And here's the deal, okay? A thermos bottle is designed to prevent heat transfer. In other words, like if you put something cold in it, you want it to stay cold. If you put something hot in it, you want it to stay hot. Now, no container can be perfect at this, but I mean, you always get some that escapes, but you can minimize it, okay? Now here, what you see in this area here, I use the rainbow to highlight it. This area in here, oops, doesn't want to let me do that. Let's see if I can do it with this. Okay, pardon me for a second. Whatever, we'll just use the black color. All right, so in this area in here that I'm coloring in black here, there's a vacuum. Okay, now the vacuum means there's no air. So there's a little sealed glass sort of container, and in between the panels of glass is a vacuum. That's to minimize conduction. So your heat transfer by conduction. This container is designed to prevent heat transfer. Okay, now your lid here is designed to minimize convection. So if you had something hot in there and you take off the lid, well, the heat will rise, and it will rise right out of the container. Okay, the silvered surfaces, so like shiny silver surfaces, this minimizes radiation. So if the substance gives off, let's say, infrared light because it's warm, well, that light gets reflected back inside. Okay, and so here we can see that all three things are taken into account when we build a thermos bottle. Okay, you want to prevent conduction, convection, or radiation. Okay, so there you go. That is, now we've done three basic definitions. This one's also measured in joules because it's a transfer of thermal energy, so the amount of energy transferred would be measured in joules. Okay, temperature is the only one that's not measured in joules here. Okay, the other two are forms of energy. So now that you know these three things are, we have to talk about something else. So I'm going to move this guy, if it'll let me, because it's really being weird about this right now. Okay, so I'll have to use my keyboard. Okay, so I'm going to move this down here. We need to talk about something else now called specific heat capacity. You'll pardon the technical glitches. I don't want to restart the video. So I'm going to move this down here to the bottom of the note. All right, so here we're getting well here. Okay. All right, so I'm just going to move this over slightly. now let's talk about something not completely new, but something related to all of this called specific heat capacity. Okay, and we're going to finish the lesson with this. Okay, I'm just going to define this for you. The definition of this, it's the amount of heat necessary. It's terrible. To raise 1 kilogram of an object. To raise the temperature, I should have said. I'll just put in a little temp. Okay, so the temperature. I'll just write it again. I'm sorry. Okay, to raise the temperature of a 1 kilogram object by 1 degree Celsius. Okay, or Kelvin, which happens to have the exact same size of unit. Okay, so that's why we kind of prefer Kelvin. All right, so take a look. There's a little table here. I got this from your textbook. So for example, water. Water is going to come up a lot. Water has a specific heat capacity of 4,180 joules per kilogram of water. Okay, so what that means is it takes 4,180 joules. Okay, I'll erase that little circle there. 4,180 joules to increase 1 kilo. Let's say you had a liter of water, which is the same as kilogram. You want to heat it up by 1 degree. Well, it's going to take 4,180 joules to do that. Okay, now is that a lot? Well, I mean, it is what it is. Most of these numbers are smaller than that. I think all of them on this table are smaller than that. So metals tend to have very low heat capacities. So here, iron just takes 450 joules. That's almost 1/10 of what it takes for water. Okay. Now, it's not a coincidence that that's a very good conductor. Lead is also a good conductor of not only electricity, but of heat also. Okay. So objects that have low heat capacities tend to heat up very easily. That is a sign that you're a pretty good conductor. Water is actually a relatively poor conductor of heat and electricity, unless you add salt to it, and then it becomes a better conductor, at least of electricity. Okay. Aluminum, 920, so it is quite a bit lower than water, but much higher, almost double what iron is, for example. Glass is somewhere in between. So it gives you some sense. Okay, of specific heat capacity. If you contaminate the water by putting alcohol in it, it lowers the heat capacity substantially. But this is pure alcohol. That would have 2,500. Oh no, it's probably alcohol mixed with water. So 2,500 joules per kilogram degree Celsius. Ice, so when you freeze water, it has a better conductivity and lower heat capacity. Okay, so heat capacity, the amount of heat necessary to raise a temperature of 1 kilogram object by 1 degree Celsius. Now, there's a formula that goes with this. Okay, and it looks like this. C equals Q divided by M delta T. Okay, now I'm going to define these variables for you. C is called the specific heat capacity. I hate writing this word. These words, specific heat capacity. So I am going to just use specific heat capacity like that in joules per kilogram per degree Celsius. Okay, Q is heat in joules. Okay, M is mass in kilograms. We're used to that one, right? And delta T finally is change in temperature. And that one is in degrees Celsius or Kelvin, doesn't matter. Okay, sometimes we write T2 minus T1, which you would expect, okay, grade 11 student to understand that. Final temperature minus initial temperature. So it's a change in temperature. All right, so sometimes we write this formula a little bit different. a little bit differently. So it's Q equals MC delta T. And this, I'll put in a box, is our formula for really that you're going to be using in the assignment. Okay. Now let me give you a few examples of how to use this, and then we'll get to the assignment, and then that'll be it for now. Okay. All right. Number one. Let's say you're going to cook pasta today. Okay, and you put 2 liters of water. I'm just going to say note before I do these examples. 1 liter of water is 1 kilogram. Okay, that's for water. Now anything that basically has water in it, so whether it's alcohol, etc., but in the liquid state, 1 liter is 1 kilogram. Okay, ice has a slightly lower density, that's why it floats, but anyway, you don't have to worry about that. Okay, so look, 1 liter of water is 1 kilogram. Okay, and that you're going to need that in the notes. So let's do some examples of how you use this. And example number 1, let's say you have a mass of 2 kilograms of water. And you put tap water in it, and its initial temperature is 15 degrees C, a little bit colder than room temperature in the tap, right? You're trying to raise the temperature to 100 degrees C because you want to boil it, okay, to make your pasta. And what you're wondering is, how much heat would that require? Now, one thing that you'll always be given is a table like this. So we look up the specific heat capacity of water, which we're going to need, and it's 4180 joules per kilogram degrees Celsius. We got that it's given from the table, okay? Now, if we were in class, I would make you do a lab, and in fact, I might give you some data and get you to determine the specific heat capacity of something. We'll do that later, okay? Like it's a pretty simple lab. Like I'll just do it for you and show you the experiment. All right, so look, how much heat will it take? Well, Q equals MC delta T. So that's equal to 2 times 4180 times 100 minus 15. I mean, this is pretty simple. I think you're going to find it easier than what we were just doing. So 2 times 4180 times 100 minus 15 is 85, and I get 710,600 joules. Okay, now in case you're wondering, if I had a 1000-watt microwave, that would take actually 11 minutes, almost 12 minutes to boil that water. Okay, it would take even more than that actually. That's a lot of water. Nobody puts 2 kilograms of water in the microwave. If you're just putting a cup in there, the cup might have 300 mils in it, a tiny fraction of 2,000 mils, which was equivalent of 2 kilograms of water. Okay, 2 kilograms like putting a huge pot of water in there. So it would take about 10, 11, even more minutes because the microwave is not 100% efficient. So there you go, there's example number 1. Okay, let's talk about another example here, number 2. I haven't mentioned power to you yet, but in grade 9 we talked about power. You should have in your science class too, but I'm going to remind you what power is. Okay, power is, in this case, heat divided by time. Okay, in general, okay, you could write power equals energy divided by time, or you could write power equals work divided by time. Like it's work or energy, whatever. In this case, it's heat divided by time. So there's power is the rate that you're using energy, okay, or energy is being transferred or whatever. Okay. So units of power are watts, and 1 watt is 1 joule per second. Okay, so you can see here you're taking energy and dividing by time in every case, so it's joules divided by time. This last one here is work divided by time. Okay, don't confuse the unit with the variable work and W. This is watts, right? And we use capital W for watts. All right. So you're going to see power showing up in the questions. Okay, let me give you an example. Let's say you want to heat up your coffee cup. I don't drink coffee, I think it's disgusting, but let's say you have a cup of coffee. Okay, and let's say someone has let it sit on the table and now it's at room temperature. First, I'll give you the mass of the coffee. Let's say it's 300 grams. Okay. Its initial temperature is 20 degrees C. You want to get it to a nice drinkable temperature of 80 degrees C. Okay. Now, it's mostly water, so we're going to use 4180 joules per kilogram. Anything you drink, you can basically treat the specific heat as water. It's mostly water anyway. Okay. And the question is, how much time will this take to heat this up in the microwave? So time for heat. Okay, heating in a 1000 watt microwave. How much time will that take? Okay, you want to get from 20 to 80. How much time? And most microwaves are around 1000 watts. So this is relevant for you. Put a drink in there, you want to heat it up. How much time will it take? Okay, all you have to do is, first we'll solve for Q. So Q equals, we'll do this step 1, MC delta T. So I'll put in all the numbers. This 300 grams is 0.3 kilograms. Make sure to change it. Okay, so you get 0.3 times 4180. And from 20 to 80 is 60 degrees Celsius, so times 60. And I get a number. 0.3 times 4180 times 60 is 75,240 joules. All right, now step 2. Power equals Q over T. So T is time, okay? And power is measured in watts. Well, I know that the power is 1000 watts, so I'm going to write 1000. Looks like 7,000. 1000 equals Q over T. Well, I know what Q is. I'm sorry, I'm writing so many little steps. 75240 divided by time. So I'll let you work your algebra there, and you end up getting 75.24 seconds, which is about a minute and 15 seconds, right? 1 minute and 15 seconds, which is probably pretty reasonable, right? So you've got this pretty big cup of coffee. Okay, that's a 300 mils would be a large cup of coffee. To get it from 20 at room temperature to 80 degrees Celsius, it's going to take about a minute. And water is especially time consuming to heat up in a microwave, by the way. Okay, now maybe you don't want it that hot, so maybe don't put it in that long. But to me, based on my experience using a microwave, that seems pretty close to being reasonable to me if you want a hot cup of coffee or something, okay, or hot chocolate. All right, so there's example number 2. Okay, so based on these 2 examples, you can see how you do questions like this. Okay, and what I'm going to do is I'm going to stop this video here now. There is a more difficult type of problem, but what I'm going to do is I'm going to let you do the assignment. Okay, so what I'm going to do is I'm just going to add the assignment here now. Okay, you can see how I do that. Okay, so I'll add the assignment, and what I'd like you to do okay, so you'll see it show up here. What I'd like you to do is just try out some of these questions, okay? Now, they just give different unknowns, okay? And you have to just work it out. Now, some of these are based on method of mixtures, it's called, okay? So I'm gonna highlight, they're not in any particular order, okay? So what I would like to do is I am going to highlight questions that I would like you to do. Yes, it's working. Okay. So I would like you, for now, do this one. Okay. Do this one. Do this one. Okay. And do this one here. Okay. So you can do 4 of them, and then I'm going to ask you to leave 3 of them because those other 3 are more difficult. I also would like you to do in the homework outline. If you haven't done these, you can do these. Okay. We already did the worksheet, so we are done up to there. We did that already. You should have done this already. Now you may not have done those, but you should have done that as part of the last thing that we did. Okay, but I would like you to do these questions here. I'm just going to highlight them, just the first few things. Okay. I'm going to put another lesson up tomorrow that explains how to do the other questions. Okay, actually I'll highlight this too. So I'll give you a couple of days to do all this, but tomorrow I'm going to put another lesson that just has examples of how to do it when you're mixing things together. It's called method of mixtures. All right, guys, so enjoy the rest of the day. I would get started on some of this homework, okay, from thermal energy and heat. Please, if there's any questions on mixing 2 things together, skip those for now, and then I will show you how to do that tomorrow. All right, guys, have a great day.